All right, so yesterday we did a bunch of examples of curves where we were discussing, can we, near each point, think of the curve as being represented as y as a function of x, or x as a function of y. And so I promised you we'd do examples with surfaces today, and I have mathematical pictures to show you. But I want to start then by giving you the general definition, which is the point of what we're doing at this point. Bad seconds. So, definition. You say M sitting inside Rn is a k-dimensional manifold if in a neighborhood of each point it can be represented. So I'm talking about doing this locally, not on the whole thing at once, but just in the neighborhood of each point. Near each point I'm saying I can represent it as a graph of a function over one of the coordinate k-planes. So this sounds abstract, but I'm going to talk about examples in a sec. If it can be, in the neighborhood of each point, it can be represented as a graph of a C1 function phi from some open subset. Sorry, Cal. So here's my open set U to Rn minus k for U, an open set in one of the standard coordinate k-planes. All right, so what is all this saying? Yesterday we were talking about curves in R2. And we had pictures, for example, we had a picture that looked something like this. Well, it didn't quite look like that, but almost like that. It was shifted, yeah. And so the question would be, is it true? So think about how many degrees of freedom you have moving on such a thing. Wherever you are, it feels like a curve, which has how many degrees of freedom? 1. So the way to think about that is that you should think about, at this point, I can find a neighborhood which is a graph over a little interval on the x-axis. So in this case, the x-axis is one of my standard coordinate 1 planes. If you're in R2, you have 2 coordinate axes to choose from. You have x and you have y. And what I'm saying here is, to be a one-dimensional manifold in R2, I need to know that in the neighborhood of every point, I can represent it as a graph either over the x-axis or over, in the cases of points like this, as graph of a function of y. So in that case, the interval would be on the y-axis. So when you're in R2, you have 2 choices of standard coordinate axes. If you're in R3, if you had a one-dimensional manifold, what would be your choices? If you had what ought to be a curve in R3 would be a one-dimensional manifold if locally it's a graph over what? You still have 1 here, so what are the coordinate 1 axes in R3? X, Y, and Z. Right. So any curve in R3 would be a one-dimensional manifold if in the neighborhood of each point I can represent it as a graph of a function over the x-axis, the y-axis, or the z. So what do I mean by a graph? I mean that if you used, say, the y as your variable, you'd be giving two functions here, and what you're giving is x and z as functions of y. So you're representing it as locally. X looks like phi1 of y looks like y, and z looks like phi2 of y. So this should be reminding you exactly of writing, using y as your free variable and getting x and z in terms of y when we were doing linear equations. Now it's just not linear necessarily. What if you were doing a two-dimensional manifold in R3? K equals 2, n equals 3. So I want to think about, for example, a sphere in R3. Or I might want to think about a torus sitting in R3. Those should be examples of two-dimensional surfaces, or two-dimensional manifolds. How many choices of coordinate, standard coordinate two planes do I have?
3.
I could do xy, I could do xz, or I could do yz. I have three choices. Those of you guys who know about n choose k's from Pascal's triangle should recognize that's what's going on here. We'll get more of that next semester. Yes, sir?
So would a plane be a manifold? Or like,
A plane?
yeah.
Sure.
Okay, I was just wondering.
Yeah, so subspaces or translated subspaces are the simplest possible cases of manifolds. They're globally representable as in this form.
Okay.
But what we've seen with curves is that locally you can do it, and then as you move around you have to switch which is your reference coordinate axis. That's why it's local, right? So in a neighborhood of each point. Nick, were you going to say something? So I told you a theorem yesterday, which we will prove next semester, that said in the case of one equation in Rn, so yesterday we stated that if you had f mapping Rn to R, and we looked at a level set where the function was 0, we said provided the partial of f with respect to one of the variables, namely xn, wasn't 0. And we had n yesterday. We said provided the last partial wasn't 0, we can locally, near A, write m as the graph. Xn was a function of the remaining variables. That's what I had yesterday. So we said as long as you had a particular partial not equal to 0, you could write it as a pivot variable on your hypersurface, on your set where f is constant equal to 0. So this is a special case of what I was talking about here. But what would the k be? So in this case, M is a blank dimensional manifold. If we can do this for every A, what's the k? K is telling you how many free variables you have. You're parameterizing. So in our case there, here u is sitting inside a coordinate k plane. That's how many degrees of freedom you have, is the k. Here we have how many? n minus 1.
So earlier you were talking about choices for our coordinate gateway.
Right.
So that's not the same thing as.
Well,
as the-
here we chose x1 to xn minus n minus 1 plane because we had this one partial derivative condition.
Okay. But we, okay.
Now extrapolate from that.
We had,
Suppose it happened as we had in some of our examples that that this partial did vanish at some point, but some other partial didn't.
you can still do.
You could permute your notation, and if it was partial with respect to x3 that happened to be non-zero,
You have x1.
you could solve for x3 as a function of all the other variables.
So as long as all the partials are not zero.
Get the English correct, Mr. English major.
As long as all the partials at a certain point aren't zero.
No.
All other.
This is one of the big problems with mathematics.
As long as not all samples are zero.
As long as not all of them are zero, as long as some partial derivative is non-zero at each point. Right, so you see what I'm
Yeah,
distinguishing?
I think I understand.
The way you said it, you were thinking it correctly, but you said as long as all of them are not zero.
Oh, yeah.
You meant as long as not all of them are zero.
As long as there exists a non-zero partial.
Well, we don't have to be that flossy about it, but. So,
Thanks, Cameron.
generalizing what we said, if M is a level set of a C1 function, and at each point in M, for some I, the partial with respect to xi at that point is not zero. You notice I'm saying for each A, there's an I where the ith partial isn't zero. Then what can we conclude? Well, when this condition is holding, for some choice of coordinate n minus 1 plane at every point. So it will be an n minus 1 dimensional manifold. Now, yesterday, one of our examples was the curve that looked like this. And what did we notice actually happened to the f at that point?
It didn't work.
This was the origin, and what, in fact, was the derivative of that f at the origin?
0, 0, 0,
0, 0. So this criterion is failing, because at this point both partials failed. And in fact, we're seeing that this thing is not a one-dimensional manifold, because we talked yesterday about how if it looks like an X near the origin, you can't have it work with either the horizontal line test or the vertical line test. So it can't be a graph over either axis. Both of those have failed. So this is not a one-dimensional manifold. But if I came in and surgically removed the origin, what do you think now?
It would be.
Now it is, right? We took away the one back point, and at every other point, one or the other of the partials isn't zero, and you can see that it is locally always a graph over either of the one of the axes. Here it's fine, here it's fine, here it's fine, here it's fine, here it's fine. All right. I want to do one more generalization, and then we're going to do nothing but examples for this today. Further generalization. So we've been talking about one pivot variable and the rest free. What have we been doing in linear algebra for the last couple of weeks? Multiple pivot variables. In other words, having different ranks for our matrices. So suppose Now, instead of mapping Rn to R1, as we did yesterday, so here I took Rn mapping to R1. I forgot to write that back down. Suppose I took multiple functions. So for example, suppose instead of just describing the temperature function as we move around in space, I do temperature and barometric pressure. So thinking about both of those, I'm mapping space to R2. And I could say, let's look at the points in space where the temperature is 73 degrees Fahrenheit and the barometric pressure is 30 inches or what, I don't know what a good...
400 total.
One atmosphere, okay. So look at the set of points in space where you constrain both the temperature and the pressure. Heuristically, what do you expect to happen? You expect to happen that fixing the temperature puts you on some hypersurface, namely a surface in 3 space. Temperature equals 75. And heuristically, you expect that barometric pressure will vary as you vary in altitude, for example. It won't vary very much, but it does vary. So that if you fix the barometric pressure, intuitively anyway, you expect that there'll be some other surface where the pressure is a certain amount, fixed amount. So what will have to happen for both of those to occur? You'll be on the intersection of those two surfaces. So what you expect to happen, as you did with linear algebra, with the linear equation case, you expected that if I wrote down one linear equation in R3, I would get a blank for the solution set. One linear equation in R3. You expect a plane. If you take a second linear equation, as long as it's not redundant, you get another plane and you're intersecting those two planes and you're getting the line, and we've been learning how to write the basis for that line. That's what we've been doing for the last few weeks. So as long as you're in the Department of Irredundancy department, you expect plane, plane, and a third plane to give you independent conditions, and so you would cut down dimension one time, one dimension each time. However, if you have redundancy,
It doesn't work.
you only cut it down as many times as you have rank worth of equations. So what would you think if I wanted to get a k-dimensional manifold? What do you think I should have for M? Just motivate yourself by the linear case. If you wanted a k-dimensional plane for your intersection, how many linear equations would you need? N minus k. So with M equal to n minus k, we will get a k-dimensional manifold for the solution set. Provided my equations are not redundant. What do you think I should look at to turn back to linear algebra? Well, you should take df to do the best linear approximation of your function. That's going to be a what by what matrix now.
N by
N minus k.
So m by, which we're saying is n minus k, by n. And if you want those, think of the linear case now. If you have an m by n matrix and you want the rows thought of as equations to give you independent equations that are not redundant, what do you want the rank to be?
N minus k minus 1. K.
If you want these to be non-redundant equations you're getting from your matrix.
And minus k.
You want rank equal to m, the number of rows, provided it has rank m, which is n minus k here, at each a. What does that coincide with what we said here? What are we saying in the case of a map to R1? Then df is a 1 by n. And what did we say that at each point some partial should be non-zero? That's saying this matrix isn't the zero matrix.
Has a rank of 1.
So it has rank 1.
Which is n.
And now I want to say this rank is as big as it can be, namely the number of rows. Okay, so let's now do examples. And the warning, the caveat here is, I know this is a whole lot of stuff to be absorbing in a few days. This is a first pass at it. The point I'm trying to make is analogy with all the linear algebra we've done with null spaces and ranks. But we will spend several weeks on this solidly in the spring and use it more in the spring.
This might be a good time for this question,
Or it
but
might not.
it might not. What is on the cover of our book?
Ah,
How is that a manifold?
is it?
Eyeball that.
It's an intersecting plane.
If you look, doesn't it look like it has
It passes
things
the-
crossing like this thing crossed?
Yeah.
Yes.
It doesn't have, it
Oh,
passes
so
the,
it's not.
It is not a manifold because of those crossings.
Why'd you?
This is actually,
Seems like an imposter.
it is an imposter. I am going to actually put you to work with taking pictures of the screen in a minute. So this actually comes from complex analysis, this picture. It's actually coming from what it's related to what's called a Riemann surface, which is a graph of a multi-valued complex function. So,
And now you know.
to actually tell you exactly what parametric thing I used to plot that I've forgotten, but I can dig that out. Okay, examples. And I actually, so I want to think about,
What's your burning question?
I sort of want to do the most interesting thing in the dimensions we're talking about. Let's do R3, and let's take two surfaces, just like what I was talking about here. And let's try to analyze, can we tell if the curve along which they intersect is a good curve or not a good curve? What do I mean by good or not good? I mean, good would mean it's a one-dimensional manifold, bad would mean, or not good, would mean it's that sort of phenomenon, something's going on. All right, so I'm going to start with one that's actually in the book. And then I'm going to do a second example, and we'll see how we do for time. And this is where I wish that the screen did not take up most of the blackboard, because I would like to show you pictures, but I also need to do work on the board, so I don't know what I'm going to do about it. Examples. Doesn't work there. So I want to look at F, now mapping R3 to R2. And what I have in mind, so I'm going to write down a function of 3 variables. And you're going to tell me what the 0 level set looks like. Suppose I'm considering F inverse of 0. So I want this equation, this function to be 0, and this function to be 0. So I'm looking at a point is in that level set if and only if x squared plus y squared is, and,
Or x squared, c squared is equal to
so this looks like what we've been doing with systems of equations. The only problem is
They're not linear.
they're very much not linear. What do you think these surfaces are?
Those look like circles. Cylinder.
Be like a torus?
No.
So-
Well, in the xy plane, this is a circle.
Right.
What is it in 3 space?
Is it, it's like
A sphere.
no, it's like a.
Cylinder?
It's a cylinder, right? You're taking a cylinder of radius, a circle of radius a in the xy plane, and then you're letting z do whatever it wants. That's a cylinder. Now, what's this one?
It's a different cylinder. Different cylinder.
On the y-axis.
It's a cylinder that runs along the y-axis. So, depending on what the radius is, you might take a little circle here and hollow out a tube that goes in the y direction. So this would be radius b, and this would be radius a. And my artwork is not very good here. If we just drew 1/8 of it, we could draw a better picture. If we just do the amount here, so I'm looking at just the stuff where x, y, and z are positive, and then I took my little orange one and looked where x, y, and z is positive, it would go like this. And can you see how they're intersecting? Where are they intersecting?
Curve along the surface of the.
Looks like here and here, right?
And it's some kind of curve.
And there's some kind of curve on there that's not necessarily so flat, but it's in both of the surfaces. And then you have 4 of these pieces that fit together here, and then there's another 4 on this side. So I will show you pictures of this. Do you think you're going to have a nice one-dimensional manifold? Do you think it's going to be a nice, well-behaved curve?
It might be as long as A is like the same.
What do you think is wrong with A and B being the same?
Then they create like an X at like, two.
They only have
Up at the.
Yeah, if you,
intersecting of.
Yeah, that's a good.
I don't know how to explain it very well, but like, if you look at the, because it looks like
They're both gonna touch at the top. And the bottom.
So if we took the case where A is B,
Then you're gonna end up with.
then at x equals 1 and x equals -1, there's going to be an X. That's what I meant. There's going to be an intersection.
The next.
Matthias wins the prize, actually. But are you guys believing him?
Yeah, no, that's a good call.
Thanks.
So if the radii are exactly equal, that means these things are going to intersect there. And now what you see is that the curve is going to do something like this. But then
On the, then when it reflects.
It's gonna do that 4 times.
it's going to do that 4 times. And the question is, do they fit together nicely, or is there an angle? Well, in fact, there is an angle here. It's not coming in flat. It's coming in at some sort of 45-degree angle.
Which is bad.
So I will show you the pictures. So let's do the math, and let's see what happens here. So what am I supposed to test? I'm supposed to take df and get a 2x3 matrix. Okay, so we're combining all our stuff on linear algebra with all our stuff on calculus at this point. What's df? Read me across the first row.
2x.
2x plus 2y.
2y space.
No, just 2x.
Same for that.
So 2 isn't very important. I know we shouldn't belittle him, but we'll just take out the 2 and just look at that matrix. And the question is the rank of this matrix 2? That's what I'm asking. Do I get independent linear equations imposed by this derivative matrix? So the question is going to be, at every point of M, did I name M?
Yes.
Now I named M. At every point of M, must the rank of this matrix be 2? Well, I can tell you an XYZ for which it's definitely not got rank 2. 0, 0, 0, 0, 0, 0, 0, 0. Right? If X and Y and Z are all 0, then I have the 0 matrix. But, well, what should we say about A and B over here?
Non-zero.
let's say these are actual cylinders, so they have a positive radii, well then the origin won't be on that set.
Right.
Now is there any other way that this matrix could have rank that's smaller?
X equals A equals B.
Hmm?
X equals A equals B.
X?
The
Alright,
case.
okay, so so think about this matrix. How could it fail to have two linearly independent rows? Well, neither row can be 0, because we,
Right.
oh wait, could,
But if
No, not
Y
it's
is
not
B.
equal.
Y and Z are.
you can't have x and y both 0, and you can't have x and z both 0. So the rows can't be 0, but could they be linearly dependent?
I mean, X could be basically Y and Y and Z.
Because that's.
We can't have either row equal to 0, but could they be
X is yeah.
linearly dependent?
If Y and Z equals
If y and z could both be 0, so if y and z are both 0, I can have only one pivot, right? Because I have x, 0, 0, x, 0, 0.
But then X has to equal A has to
But then x would have to be having its square equal to a and its square equal to b.
So
So
A,
you
B.
see Matthias's point exactly now. If x is either a or b, it will work, well, or it will satisfy this condition, but only will satisfy the second equation, so it will only work for both equations when A and B are the same. So something's fishy when A and B are the same, and Matthias has already picked up on that. When A and B are the same, we do get the rank dropping at 2 points. But can you now convince me when A and B are not the same, this rank can never be less than 2?
Yes.
Yeah.
Because then Y or Z has to be non-zero.
So you can't have y and z both be 0. We've just established that. And
Right.
so at least one of them must be non-zero, which means you have a pivot
In X. And-
in that column or in that column, or
Right.
both.
Or both.
And in the first
Agreed? Well, if x were 0, you would have the pivots here.
Right.
And if x isn't 0, you have one pivot there and one, so you have a pivot here and then,
that becomes.
Well, you'd have to look at it
subtract.
coming the other way. You'd have a pivot in Y, or a pivot in Z, or a pivot in Z, or Y and then X, or Z and then X.
so if x is 0, both y and z are not 0, so 2 pivots. And if x isn't 0,
Y or Z is.
one of y or z must be 0, but must be non-zero. If x isn't 0, we cannot have both y and z 0. So that means either this isn't 0 or this isn't 0, so you're going to have x not 0, so you're going to have a pivot here. And if y is 0, then z isn't 0, so you have a pivot there. Now what if z is 0?
Then
Then
You-
switch the rows,
Yeah.
and you have a pivot here and a pivot there. Everybody following this? There are better ways to think about this, which you'll discover as we play with this more. All right, so let's actually, let there be dark. Okay, are you on?
Yep.
Well, this is not, this is the second example.
Looks like a golf ball inside of a toilet paper.
So here are my two cylinders. So here's the picture, the way we were doing it, where B is smaller than A. And it looks, we're looking on it end on here, but this is what we were seeing, right? You see this curve here, and there's one on the back. So now what happens as we shrink the tall cylinder? Well, the curve of intersection now moves symmetrically onto the other, around the other axis. There's one there and one down here. But what happens exactly when the radii are both 1?
You can type in 1.
There you go.
So now let's see it. There's Matthias's X. Marks the spot. So what does this remind you of? That the curves are moving from living on one, going around one cylinder here, and then as I go change my parameter for the radius, I get my X, and then what's happened? The curve's going around the other cylinder.
Yesterday.
Okay, it's sort of like yesterday's, which I'm going to get back to in a sec.
Is it
But this should remind you of
the sides?
Parametric equation, hyperbola thing?
the hyperboloid, the saddle surface sections, when we looked at level sets of the saddle surface, f of xy equals x squared minus y squared, and it went from one set of hyperbolas to the other set of hyperbolas, and in between it was two lines. This is exactly the same phenomenon here. Now, while I have the picture up, yesterday we were talking about the two different cubics, and I promised a picture. So remember, we had a cubic that had two pieces to it. We had the cubic that had the two pieces, and then we had the cubic that just had the one piece. And what happened as you went from one to the other?
There's a point in there, yeah, okay.
So what's happening right as the parameter goes through the value where you go from one kind of cubic to the other, you're getting the
X.
the X, which,
Click on the downish arrow thing, maybe.
so, moving right,
Yeah, it's there.
oh no,
It's there somewhere.
it's there.
There, that looks like it.
There it is. So that's the one with the X, and if you vary the parameter that I have in this to the left, you get the two-piece cubic that we were doing yesterday, and then if you go the other way, if you go far enough the other way, the second piece disappears. And you have just one piece. Okay, so I want to do the other example of surfaces intersecting, which I'll go ahead and show you the picture of just because I only have so much time here. So the other picture, we're going to take a cylinder and a sphere. And the question is going to be, again, as you deal with the radii, what do you think is going to happen with the intersection of the cylinder and the sphere?
It's gonna make an X on the back.
So here's another one where we can sort of think of a little movie here. Here's the sphere that's small compared to the cylinder. Now watch what happens as we make the sphere get bigger. If I make this really big, that's again like what happened with the two cylinders. You now have a curve up here and a curve down here. If you make the sphere really small, then in fact there's just one curve that's going around here. There isn't. If I look around the back, there ain't nothing. But what happens in between?
Makes an X on the back.
Shouldn't she get to point 2?
So what we really should be doing is sneaking a look around the side of it we've got this nice curve that's meandering around.
Make an X.
Got this nice curve that's meandering around and making like an indentation. It's one curve now, right? You see it? Goes along here and goes around the back and bends in, but now watch what happens as I inch forward slowly.
Wait,
Not slow enough.
Too fast.
Back,
Back 10.
It switched already. Go to 2.0.
I think that's what we want, right?
Yeah.
It's not 2.0. There it is. There we go.
And there's the x. All right. So again, when you're having special values that make redundancy occur, but if you have non-special values, you're going to expect to see irredundancy. Okay, so I want to show you. Come on, turn off. It's off. It's off. So let's do that. So you will have some homework where you're doing exactly this stuff. I don't believe you actually need to be able to draw beautiful pictures to do it, but if you want to go on mathematics and draw pictures to see what's going on, you're certainly welcome to do so. So now I'm doing a cylinder and a sphere. So let's take the unit sphere and let's take a cylinder that is going, so this is looking like in the XY plane I've got a circle that's sitting centered here. Do you see that? Actually, I'll put a 2 there just to make life better. So this circle is centered at 0a, and it passes through the origin. So you can see that this circle, if you complete the square, this is x squared plus y minus a squared equals a squared. And you set this equal to 0. So that's a circle centered at 0a of radius a.
Wait. We don't have a radius.
So now, I'm not drawing the z stuff, I'm just drawing the xy plane. Now the sphere is coming from something that could look like a big radius circle here, or a small radius circle here, or the interesting one is when it just crosses there. That's when you expect something funny is going to happen. That's when you expect the cylinder and the sphere are going to be tangent, and that's what you were seeing in that picture, was when you got the x. So let's just do the algebra here. Take the derivative. Two x, 2y, 2z, 2x. Zero. So once again, I'm tired of the 2's.
Terribly double done before there,
And we want to know, could these vectors be linearly independent or dependent?
Yes.
If you think about the rows. So could this vector be 0?
That would be
Only
within
the
the
origin.
cylinder, but not the sphere.
Oh, no.
Right? You can't have 0 on the sphere.
The unit.
So the vector xyz can't be 0.
Right.
What about the other vector? Could that be 0?
Yeah.
Yeah.
Be careful.
No.
No, because x can't be.
Look at this equation. Yeah, I'm assuming A is positive here, by the way. Right? This vector, this equation says that this vector is not, has length A.
In your equations, are we varying the size of the sphere or the cylinder?
Here I'm varying the cylinder. On the video, on the mathematic, I vary the sphere, sorry.
But if you're varying the cylinder, wouldn't the sphere be in the center and then the cylinder be expanding outward so that the graph would look slightly different?
Yes, you're right. So I lied. You're right. This thing is what's changing. The sphere is sitting fixed, and the cylinder's changing. So this is moving. Yeah, sorry. Good. So this fixed sphere, and the cylinders. Yeah, thank you. The cylinders are looking like this. And then the interesting one is, again, the tangency when it looks like this. Yeah.
Sorry.
No, you're absolutely right. That was my mistake. Erase the tape. Okay, so these vectors can't be zero. But could they be linearly dependent?
Yes.
They could conceivably. But I'm now going to be sneaky. Just the right amount of time to be sneaky. What's the dot product of these two vectors?
X squared plus y times y minus ay.
Weird. It's almost like
That looks a lot like our equation right here.
minus AY.
It's almost exactly.
That's interesting.
Two on the outside maybe?
A squared.
Is it kind of like a cylinder
Oh,
that's
no,
not
it didn't
quite-
quite work. So it didn't quite come out the same as what we had here. So that didn't work. That trick didn't work. But that's something you might look out for as you're doing homework. So didn't help. What I was hoping to see was two non-zero vectors that are orthogonal. Must be linearly independent by your homework. But I didn't get to do that, rats. But you could still do row operations here very easily. Kill the x.
0 minus a. Or minus a.
So I for sure have a pivot here. And right? Because a isn't 0. Could it happen that both x and z are 0?
Yes.
Sure. Zero.
So if we had x and z both 0, then we'd be in trouble. We'd be down to just one pivot. But if x and z are both 0, that means y has to be 1 or minus 1.
Oh, I see, yeah.
And then your second equation is going to hold if and only if y is
A is y.
A is
1/2.
1/2. Just 1/2.
so for
Yeah, that makes sense.
this equation with x equal to 0, I have to have y minus y has to equal a.
No,
something's
that won't
wrong.
work.
Y equals A.
Y equals a over.
No, 2A. Y equals 2A. Yeah.
Y equals 2.
No, y has to be 0.
Oh, no. Y can't equal 0 and plus and minus 1.
Right.
Not happening.
Y equals 2A.
Not this
0.
equals
See,
1/2.
X equals 0.
The problem.
X equals 0, so y squared minus 2AY
A
equals 0.
equals 1/2.
A just equals 1/2, that's all.
No.
Hang on.
I like, yeah.
So if x is 0,
Right.
And we know y is plus or minus 1.
Y is
So A is 1/2.
all right.
Plus
so-
or minus.
So then you would have, I mean, what I'm trying to get at is in the one situation where A makes the picture look the tangent here, so that would be the case where A is a half, which is what you guys were saying.
Because it's y minus A equals A, so y equals 2A.
So,
Y is 2a, but y is
Well, we
1.
can't, if X
Y is 1, so it has to be half of y.
this can't happen unless A is a half,
Plus or minus half.
plus or minus a half. in which case you're getting the tangency that we saw in the picture. And if A is anything else, this matrix has rank 2 for all points. Okay, sorry about that. Have a good break. If I don't see you in office hours between now and then.